let's look briefly, this won't take long, at the area between two curves. And sometimes my classes have already seen a little bit of this. But let's assume we haven't done it before. We've got some curve, say f of x, and some curve y equals f of x, y equals g of x. And we want to get the area between. So one place you might do this might be the revenue, the sort of daily revenue, rate of revenue in for your company, and this might be the cost, maybe the daily cost. And you want to add up to get the total revenue minus the total cost, or the, let me put rate of, or the total profit, because profit is revenue minus cost. So in other words, what we want is the total revenue from the rate of revenue minus the total cost is the area between these guys. So it doesn't have to be this kind of example, just anything where you want the area between two curves. This is a place where my students have often seen it before. And the most basic way to do it is really simple. What most people come up with, just looking at this problem, you can pause the video and come up with it yourself if you want, you probably will, is just to take the area under f all the way down to the axis and then subtract off the area here. And so we just get that the area in between, this is one way to do it, it's not the only way, we'll see a slight variation of this that can be useful in a minute, is just the difference of these two areas. Now, you might want to pause again and think, is there some case where this might be a little weird? Think about we're taking the area between this and the x-axis and between this and the x-axis. So think about that. You might get skeptical. Here, I'll give away the answer. You might get skeptical if like one of them is positive and one of them is negative. Or maybe if like this one crosses, like here's f and here's g. Now if they cross each other, it is trickier and you have to specify exactly what you mean. But here's a case where one of them is positive and negative both, one of them is negative. Is it still going to work to take this minus this? It's not as obvious that that's going to work, but let's think about it for a second. This guy treats this positive, and this guy negative, and this guy positive, and this is all treated negative. So let's just segment it into three parts real quick. Here we're going to take that positive, and then we're going to subtract a negative from this contribution. Well, that's okay, because subtracting, taking this positive and subtracting this negative, amounts to adding these two guys together. Okay, that's what I wanted. I wanted this total. Here, I'm going to take this negative and subtract this negative. That turns this into positive, which we did want to count this stuff as positive, but we didn't want to count this because it's not between f and g. Oh, that's actually exactly right. This positive minus this. Okay, so it's actually working. And then here we're back to the first situation. So even if you think about it as this minus this, it actually does work no matter where the x-axis is. But there's an easier way to see why it should always work, and a slight variation on the formula. An algebraic fact we have is that the difference of two integrals is the same thing as the integral of just the difference f of x minus g of x dx. So what does that do? Well, let's draw the picture one more time. I'm going to draw it again above the axis because I want to get away from being scared of that, and this will convince us hopefully that it doesn't even matter where the axis is. F of x minus g of x, what we're doing is we're at every point value of x, we're taking the difference of those guys, which is the distance between the f of x value, remember this is f, this is g. We're taking the distance between these guys. Remember when you subtract two things on a number line, you're taking the distance between, as long as we take the bigger minus the smaller. And that's the subtle issue, that if they cross, then we're going to have to split it up into a bunch of parts. But let's assume that f is always bigger than g, and we're going to try and set it up that way whenever possible. So we take bigger minus smaller. That's going to be important. But if it's bigger minus smaller, that's this distance. And then what does this do? An integral says add up height times width. Okay, so it's the height. We can think of it as a tiny little rectangle, going back to the rectangle method. Ooh, that's kind of a fat tiny rectangle. Sorry about that. Here's a tiny rectangle whose height is the difference between f and g, and whose width is a tiny little bit, let's call it dx. So this is just the height times the width of those rectangles, and then this collates them all together, adds them up. So it's just all, we're going to take this into, use a rectangle method on this whole thing. The book goes into a more careful justification of that idea, but it amounts to saying that yes, this is going to work, and it amounts to this as well. But this is a little cleaner to see it as one integral. You don't have to do one integral, which is nice. Sometimes there's some nice cancellations that happen in here. It'd be a shame if you had like integral x to the 17th here and integral x to the 17th here and you didn't realize that those would cancel out. This lets you cancel them out better. And then it also shows that it really has nothing to do with where the axis was. F minus g is just always going to be the height of this guy minus the height of this guy, regardless of whether they're both above, one below, or both below the x-axis. It doesn't really matter. So I like the fact that most people tend to come up with this on their own, but this is a little bit more sophisticated, and this one people tend to think, ooh, this might be weird when everything's plus and minus and net signed area and all that stuff. But it always works, mainly because it's really equivalent to this one. So let's just do a real quick example. Let's say area between y equals, let's say, just real simple, x squared plus x, and y equals, let's have a purposely do a negative. Let's say minus 2x from x equals 1 to x equals 3. All right, what does that picture look like? Well, this one I'm purposely going negative, so that's coming down like this. So if this is 1, this is 3, then this is going to be minus 2 and minus 6, if we can see that. Yeah, we can still see that. Okay. And then x squared plus x is going up like this. It's a upward curving parabola. So it's this area in between that we're trying to get. Well, that's really easy. It's just the integral, this area is the integral from 1 to 3 of the difference of these two functions. Now, be careful, minus a minus, that's going to end up being plus. And here's what I meant about cancellations. This simplifies a little bit. X squared, plus 3x dx, which is x cubed over 3 plus 3x squared over 2, evaluated from 1 to 3. And I can't quite fit it in. I'll slide it in up here. Which is going to be 3 cubed over 3 is 9 plus 27 halves minus 1/3 plus 3 halves, which is some number of sixths. So that's 54 plus 81 minus 2 minus 9 all over 6. And you get 135 minus 11, 124/6, I think, which is 62/3. You can check my arithmetic, but that's not the part I'm most interested in. So that's one example, and I think I might do another video giving one other variation on this kind of idea.